Okay, so welcome everyone to our last session, and our first speaker is Dr. Clark Alexander. Dr. Clark is, of course, a very nice friend of mine. He's a co-founder of Enerjuice, a renewable energy IP firm, co-founder of Open Blackberry Network, a non-profit data and energy training company. He's also advisor for NETL, mathematics and physics in data processing, advisor of ODE L3C, a quantum computational chemistry company. He also holds multiple roles at Batch Freight, head of AI, senior director of engineering, and head of R&D. He's also have been teaching in several universities, and of course been invited to be a speaker in different events. And he has an interest in deploying blockchain with quantum and AI indeed. So welcome, Clark. The floor is yours.
All right, thank you. We'll try to keep this short. This is my talk. That's it. Okay, I'm just going to put this away. Okay. Okay, let's start with the question. I like this. And I actually want you to think about this. So if you're looking on your phone, shame. No, don't do that right now. Okay. What is the tallest tower you can build out of Legos? I really want you to think about this. What is the tallest tower you can build out of Legos? These little blocks that you play with. Who likes Legos? Hands, if you're not raising your hand, you're not being honest. Or you're not paying attention. Stop it. Okay. Who likes, what's the tallest tower you can build out of Legos? Okay, we give it maybe 30 seconds to think about it, but you'll come up with two answers. There's really two answers. There's the math answer, and then there's the physics answer. The physics answer was sort of answered about 13 years ago. In England, they built a tower 11 inches, like 35 meters. That's about it, okay? Because we're asking things like, how much can the brick handle? How many bricks do you need? How many bricks do we have? Does gravity change that high? But the math answer is, as many bricks as you want. Build it straight up to the moon. Now, what's the point? Why am I asking such a silly question to start? It's because when you're talking about trying to build a Lego tower to the moon, al-qamar, the physics changes. The rules actually change. The mathematics does not, but the rules do. So this idea of scale is very important. Scale at the level of massive things like AI, scale of miniature things like quantum. Now, the rules change, and that's important. Okay? So when we're looking at cosmological things, we have relativity, we have gravity coming into effect. When we're looking at quantum mechanics, very, very, very tiny. The geometry, completely different. It's not the geometry we look at. It's not even non-commutative geometry. It's like its own unique thing with its own unique set of rules. So if we're trying to build a quantum computer, we have to follow a different set of rules, right? The quantum software follows math rules. Programming follows math rules. Hardware does not. Follows a different set of rules entirely. Totally different set of rules. So that brings us to this question. Second question. And other Ahmed who's, yes. Quantum advantage and quantum supremacy. We hear these terms a lot. Kind of answered this a little bit. Now, let me step back really quick. In modern computing, when we're teaching at the undergraduate level, we think about two types of metrics that we measure computing by. We've heard a lot about this today, speed and memory, okay? These are kind of gone, right? We do the algorithmic analysis, can you sort in log n time, all this, right? And we realize that you can trade off speed for memory. But memory is super, super, super cheap. You can buy terabytes and terabytes and terabytes of storage. Super cheap. So that trade-off is not that important. But there's this third idea that's come up, and that's energy usage. Right? Now we're talking about scale. So, quick anecdote. A few years ago, I interviewed to work at Oak Ridge National Lab in the quantum machine learning division. And at that time, they were putting in Frontier, which we've already seen. Yes, Ahmed, right? Ahmed and Ahmed all gave me like good talking points to talk about. So, and Professor Shauki, yeah, I mean, I'm just going to guess the next reference I make is going to be Ahmed as well. So, they built the world's biggest computer at that time, fastest, and critically, most energy efficient per computation that had ever been built. So when I was interviewing, the guy talked to me, he said, the reason we didn't build this twice as big is because we couldn't afford the energy bill. And they work for the US Department of Energy, right? So we're talking like not small, we're talking like massive, massive, massive scale. And these are the guys saying energy is the most important factor, okay? So let's look at this. I'll pick on IBM real quick. How much energy does it take really to compute such a thing? Well, let me step back real quick. I didn't say what advantage and supremacy are. Quantum advantage. Quantum advantage is when you have a quantum computer that can outperform in at least one of these three metrics: speed, memory, or energy. Right? That's what quantum advantage is. We've probably seen this already. I think Marco Pistoia at JP Morgan and probably the Gaussian boson sampling probably got it in speed. I think we've achieved advantage in speed, random circuit sampling, such things. So whether these are actually useful or not, we can debate that. We can debate that forever. But advantage, probably we've seen. Now, supremacy is going to mean that we are going to achieve better results on a quantum computer in speed, memory, and energy in a large, large, large set of problems. We're not talking about floating point operations. We're talking about massive utility scale, weather prediction style things. And from my perspective, I don't think we're going to get there maybe ever. It's hard to say. But so let's look at this energy thing here. The way I want to think about quantum advantage and quantum supremacy is that, you know, advantage, we've got speed. Now, let's look at memory. I don't think quantum memory is even in the discussion yet. Anyone working on quantum memory? Like terabytes of quantum memory? No, we're not there. So that's out. That's out for a while. But so we can actually talk about energy. So this is from IBM's blog. Heron, 156 qubit processor, yes? Yeah? Okay. So on their blog, they say it takes, they've built this like amazing dilution refrigerator, which is super, super, super cool. Cool, like I like it, and like actually cold, temperature cold. It takes 25 kilowatts to cool it, and it takes 4 days to cool it. So someone do the math. How many kilowatt hours have we used to cool the refrigerator? So 96, right, it's 2.4 megawatt hours. So how much does it take to run a laptop? 50 kilowatt for 4 days? Oh, that helps me out a lot, right? That makes the energy consumption way more. So I'm going to go with 2.4 megawatt hours and give IBM the benefit of the doubt. I mean, this was on the blog, so I could be wrong. Not maybe as wrong as ChatGPT, but wrong. Okay. Well, yeah. I have energy concerns about them. You can talk to me at dinner about that. Okay. 2.4 megawatt hours of energy in 4 days. So this laptop you're using is 64 watts. So we're saying you could run at full capacity 400 laptops for 4 days to get one computation. So how much computation can you get done with 2.4 megawatt hours in 4 days? The answer is like a lot. Like, my arms don't go that far, but like, I'm gonna fall off the stage, but I am really actually gonna fall off the stage. Don't do that. Okay. 2.4 megawatt hours will do that to you. Right, that's a lot of energy, and that is a lot of time in processing. So I've spent a lot of my career working in optimizations, approximations, stuff like this. So in trading stocks, I don't have 4 days to make a decision. I've been working on supply chain optimization recently. I don't have 4 days to make that decision. It has to be done right now. And so can you get an approximate algorithm to get you there faster that's good enough, right? This is a totally different metric. I know we're talking about reliability, but in practice, in like real situations where optimization is important, reliability is like not that important. It really is not. I want to get a stock portfolio that returns for me 20%. But if I looked for 4 more days, I could find one that gets me 20.0001%. Any investor will be like, take the early one. Dude, got 4 days to invest it. We make that 0.0001% back. Right? This is a realistic scenario. So, okay. So that's the energy barrier on the top. Right? Okay. We're going to get lower. IBM's very clever. I like that they're building different qubit designs. I like that the spectral expander graphs are coming in. He didn't talk about it, but as a mathematician, I'm like, oh, right, spectral expanders are getting better connection, woohoo. Expander graphs is another thing that I work on. So, right, I can see it, how the mathematics is coming down, right? Some of the energy costs coming down, perfect. Now, let's talk about this barrier on the other side. This is where we're really getting into the quantum mechanics of it. So, third question. Anyone remember the uncertainty relation? This is for undergrads. Where are my undergrads? The sleeping one. She's pretending not to notice so she doesn't have to answer. Uncertainty relation. What is it? Anyone know it off the top of a head? Put it in your quantum computing courses. It's there. You got it? What is it? Yes, Heisenberg. My natural habitat in front of a whiteboard. What is it? What's the exact number? I'll write delta. Well, you could write sigma if you like that, if you're into statistics. Delta x delta p. Exactly right. And that only comes from the complex commutator of the operators. It's actually more than that in reality. We're not ever getting close to that. But now, let's do the numbers. That is approximately, if we go in Newton meters or electron volt seconds, we can do it this. But let me give you the energy calculation. That's about 3.1 times 10 to the minus 35 joule seconds. Yeah, you can't get below that. So here's why this is important. This tells us that quantum Fourier transforms will never, ever, ever, ever work. And Shor's algorithm will never, ever, ever work. It will not. It cannot. There's a physical energy barrier down there. Now, let's quantify it. So what am I saying? What's the quantum Fourier transform? Right? It's this thing where you have to have all the qubits connected, no interference, no nothing, all fault tolerant, all logical, everything good. And you have 2 registers, top register in qubits, bottom register in qubits, and you rotate pi over 2 to the n, right? So rotate, basically, in qubits gives us this. For quantum Fourier transform requires exactly pi over 2 to the n over 2 angle rotation. We need to rotate that angle. Okay, at 156 qubits, what's that? Pi over 2 to the 156 over 2. Undergrads, good. 78, fantastic. You guys are doing a great job today, helping me out here. That's about 10 to the minus 23, okay? This is angular, okay? So we're not quite there. Now, I worked this out for you. The most that we could ever get before we get under the uncertainty limit, 236 qubits. That's the maximum. There's an energy barrier, not a suggestion. There's like a fundamental law of nature. So n less or equal to 236. Done. So RSA, double that, so what do you get? 472, RSA 472. That's all Shor's can do. It cannot do more than that, and it's not a suggestion. Now, there's good news. I want to quote a movie from the 90s. You may know it. It's called The Zero Effect, okay? It's a Bill Pullman movie. Silly quote here, it says, if you're looking for something specific, your chances of finding it are very bad because of all the things in the world. But, this is a comedy movie, if you're looking for anything at all, your chances of finding it are very good because of all the things in the world. Okay? That's a little bit philosophical. Bill Pullman, whatever, fine. Okay? But here's the thing with quantum computing. What we've been doing right now is we've been going down this lane of annealing, and we want to find something specific there. We've been going down the route of gate computing. We want to find something specific there. Okay? Prime factorization is an interesting thing because up until 3 months ago, we had one way to define prime numbers. But now, we have infinitely many ways to define prime numbers. There's a result from Craig van Ittersen and Ono. Ken Ono, like, genius mathematician. They just put out a paper called Partition Functions Detect the Primes. So they give, with partition functions, additions of integers, a new way to detect prime numbers. This function zeroes out if and only if you have a prime. And then they proceed to show that there are infinitely many such functions. Okay, so what we've seen here is this sort of black swan idea. Right, thinking about Nassim Taleb's black swan. Stuff that you can't predict, it'll come up, it shows up somewhere, and it has a massive effect on the ecosystem. Right, what we need to look for now is any one of these infinity prime definitions that can be broken by a quantum computer. We just need one. Right, so I'm not saying fast factorization can't happen. In fact, I'm saying it probably will happen. What I'm saying is that Shor's can't. Shor's is bounded below. Not possible. Again, not a suggestion, just not possible. Okay? Yeah, so, last couple things. How do we get around this? We talked about this in depth today. Gate count, circuit depth, and then, then looking for anything at all. Those are kind of how it does. So, gate count, back in 2016, Ross and Sellinger out of Dalhousie University in Nova Scotia put this paper out called Optimal Ancilla-Free Rotations for Z-Gates. So they were looking for gates in this form. They're rotating through Z, right? But it was e to the pi over n, e to the minus pi over n. So you'll recognize that as a Z rotation if you work in gates. And so they wanted an optimal thing. They wanted to use the fewest number of gates to get there. Now, of course, when n gets big enough, we've shown that that's meaningless. Not mathematically meaningless, right? They were approximating to 3,000 decimal places, but physically meaningless. If you rotate more than this, or less than this, it is physically not readable, right? There is that barrier. But they were the first to sort of give this, we need a shorter gate count to get these rotations. Okay, so that idea has been around about 10 years now. Second thing was circuit depth. Now, there was this interesting paper from Simon DeWitt back in 2009, which probably most of you have read, an Intro to Quantum Error Correction. You may have seen this, a lot of you have probably read this. He asked this one really interesting question. What is the difference between these two circuits? Or these three, let's, What's the difference in those three circuits? There's two answers. There's a math answer, which is there is not a difference. Mathematically, those matrices multiply to give you identity. But the physical answer is, Ahmed, what's the physical answer? There's noise. There's noise. When you actually apply gates, there's actual noise. The mathematics and the physics do not agree at this scale. They do not, right? This is what really the big problem in the NISQ era is that this thing does not give you back the identity. The engineering at that scale is so difficult. So when we get these actual breakthroughs, the IonQs, the IBMs, we should applaud them because it's so difficult. The mathematics is like thousands of years ahead of where we can actually get the engineering, right? But that's an energy calculation now. Okay, I want to stop there, leave you guys time for questions. Please come talk to me at...
Thank you very much for this elaboration. But I myself, I want from you a confirmation about how do you see the quantum? So what I understood from you, quantum is not going to happen to add a value-add thing.
No, misunderstood.
Yeah, because you said that it will require energy. So I have 2 comments about what you have said. First of all, you limit the discussion only about Shor algorithm.
Oh yeah, for
You
sure.
did not consider other aspects of quantum in material science.
Oh yeah, there's lots
And
of things.
quantum machine learning, which has shown a lot of progress. So I wonder why you have limited the discussion about Shor algorithm.
Because
and you
there's
did
an
not
energy barrier there. There's an energy
Going
barrier
to
there.
the energy, speaking about the energy, we make an apple-to-apple comparison. So if we consider a classical algorithm that will take 10,000 years, you need to calculate the energy of this algorithm and compare it with the running of this quantum algorithm in a machine that can do it in 3 minutes.
Correct.
So this is the comparison. This is the apple to apple. So keep talking about energy without making an apple to apple comparison will mislead people.
It may.
It will.
Okay.
So
fine.
this is one dimension.
Okay.
The second dimension is about the value of quantum. So really, I was really annoyed by keeping the discussion about Shor algorithm. We know for a fact that Shor algorithm is only one step. And I can show you in my notes that we in IBM, we have developed many other algorithms that supersede Shor algorithm, and they will definitely factorize numbers. But why we keep saying or giving the honor to Shor? Because he was amongst the pioneers, along with Groover. And this is why we bring Shor algorithm, Shor himself, and Groover to the discussion. So really, I'm annoyed because the discussion should be scientific, and we make apple-to-apple comparison. So we need to talk about, for example, the energy consumption in the context of making a comparison between 2 problems and see how much energy they will take in order to make judgment. Speed, we consider time between 2 algorithms. And this is how we can show the quantum advantage. Also cost. Thank you.
Sure.
Yeah, please. Go
Yeah. Again, let me just say that I'm not saying these things can't happen. I'm saying they don't happen this way. Well, what I wrote before. It's not going to happen with Shors, right? It's very, very important. And part of this is because the way of how we define primes, okay? Now, material science, almost certainly we're going to get bigger discoveries, right? And again, like I said, I see that IBM has developed the circuits in a more spectral expanding way, makes me think that it's actually going to happen sooner, right? So let's not forget that, there's a lot of deep math going on here that I'm acknowledging, but, right, that one, it's the famous one, right, because it's 94. Mathematically, it's proven. I proved it in a class that I taught 8 years ago, right? Shors mathematically works. Physically, it can't, okay? Other quantum algorithms we don't know. And I think we're kind of at the point, the gentleman who spoke first this morning, his name slipped my mind. He said something really interesting. He said, we're kind of at the space where we don't know which algorithms are going to perform better in quantum and which are going to perform better in classical. We're kind of in that space in quantum right now. So the point is that I'm not sure we even know the correct questions to ask quantum computers. When we find them, it's going to take off. Very much black swan style, okay? But don't misunderstand. I'm not saying quantum can't work. I'm not saying there's not value in it. I'm saying there are strict energy barriers to certain algorithms that we are sometimes ignoring.
Yeah, this is research. We deal with challenges, and this is why we're researchers. So energy is a challenge. Error correction is a challenge. And this is why we are living in a very interesting time. We are enjoying this era because there are too many challenges in quantum computing. are living in the same time that in 1940. So we are part of the history. I'm not talking about myself. All of us, we are part of the history. So our gathering today is maybe will lead to something tangible or something historical. So what I wanted, the message from me, forget the idea. I'm a researcher at the end of the day, and I can tell the difference between what is research and what is sales or harvest. There is a lot of noise and hypes about quantum, but the beauty that we are as a scientific community with a judge, we can ask questions and we can enjoy this era.
Agreed. Okay. I think we should take this discussion to dinner.
Yeah, I think that's
I'm
for
very
good for
excited to
dinner.
continue this. Please come talk to me. I'll be here all week.
Yeah,
Try the
but I
salmon, it's
wanted to
delicious.
say that it's good to see that quantum is still in early research, and of course there is a lot of challenges, and one of them is the physical limitations, which one of this aspect is the energy, and the energy, of course, is one of the fundamental aspects of limitation of quantum. So that's so you have another question, Clark. Yeah, you have another question. Yeah, you still didn't done. Yeah, we are talking about that. It's different aspects is the research, and one of this is the energy, as Ahmed has laid down, and of course this is the energy and this is research. So, Dr. Murat, yeah, please go ahead.
Yes, thank you for very interesting. So, if I understood your point, you use like scaling law as the number of qubits increase, the phase you need in QFT becomes smaller and smaller, and at some point reaches some ground, let's say a boundary that cannot go lower.
Correct.
Okay, but this at most will put kind of upper limit on the Shor algorithm. You say Shor will not work, but
Well,
can you be more
anything
specific?
with quantum
What would
Fourier
be the upper boundary you can put according to your argument?
Well, I mean, so any quantum Fourier
Because
transform.
15 equals 3 by 5, this is what you are doing. This is very simple. So we can, Chinese, you are aware about the Chinese,
So we had this
up to 50 digits. So what would be an upper limit? Maybe not the 2048 RSA.
472. 472 is the limit.
472 is what? The number of qubits?
Bits.
Yeah, so what would be the number n equals p by q, the equivalent in Shor algorithm, compared to the RSA numbers, I mean?
Our RSA 472 is kind of where it tops out.
RSA 472.
So like RSA 512 is safe from Shor's algorithm. I'm not saying it's safe from Ken Ono's stuff. I'm not saying that it's safe from other stuff. So the upper bound, the biggest number you could factor
Yes.
purely with quantum Fourier transform, 472 bits. Before you get to uncertainty limits. Now
It's quite a lot.
Yeah, that's big.
Almost 500 digits, it's a lot.
Yeah, it's a huge number, but it's not
Yes.
RSA 2048. RSA 2048 is much,
Yes,
much.
it's
I'm
67.
gonna fall off the stage again trying to show you.
Yeah, it's 17 digits. This.
Yeah, it's huge. So we're not totally safe. Don't like, leave your laptop open without a password, right? But what I'm saying is the hype around what can be factored in the way that we do internet security now, roughly safe for the current status of what we're hearing in the news. They say RSA 22-bit was broken. I can do this with a laptop in 0.3 of a second in Python. Right? It's that 22 bits I could ask an 8th grader to do by hand, and they could do it in a week. Right? But 2048, not possible. Not with this. It's possible by some other algorithm which is not yet developed. Okay? Right? Something is going to come up that we don't know. For sure it will.
By the way, we have developed an algorithm which is different than Shor algorithm and require less number of gates and this number of gates.
Yeah, exactly. Gate depth. That was my mitigation plan. Gate depth and circuit.
So I agree with you 100% that Shor algorithm is just for application. If we wanted to implement it, I said an example. I said we need 20 million qubits, physical qubits,
Yeah.
which make it impossible. But this is a nice challenge for us. When I say us, for the researchers. So IBM responded to this challenge by introducing a new algorithm, and I can show you in a presentation what is the name of this algorithm and who was the researcher. And also we respond to this by reducing number of qubits and reducing the gates and excelling in our hardware. So there are different techniques.
Completely, and there has to be.
So this is our point of view. I'm sure that other service providers or other modalities, they have many answers for that, and maybe better than us. But the point which I would love to make, that quantum is useful. It comes with a lot of challenges, and this is our responsibility as researchers to sort them out.
Okay, thanks very much for the nice discussion. I think it was a very nice talk. Now Clark has outlined what could be the limitations, and of course from the discussion we know between Ahmed Al-Qatacha and the Clark, it's an ongoing research, and all the time it's about how to overcome those challenges by working around, as also Clark has laid down the mitigation also strategy. So thanks, Clark.